channel of Digital to Real. Today we will discuss about adders. So there are two types of adder, half adder and full adder. So we will discuss about both of them. So an adder is a digital logic circuit, okay, in electronic circuit that is used for addition of numbers. So what the adder does? It adds the numbers. Now in computer and many processors, adders are used to calculate the addresses and calculate the table indexes in the ALU. And these can be built for many numerical representation like XS3 code or binary coded decimal. So what does it mean? It means that in computer and many processors, what happens? Big addition, okay, operations takes place. We add the addresses, we calculate the addresses, we are having the offset, then we have to go to the offset address. For all these purposes, we need adders, and they are multi-bit numbers, so we need big adders. Okay, what they do? They calculate the table indexes also in ALU, an arithmetic logic unit. In order to fetch data, in order to fetch address, we have to calculate the table indexes. So that for that purpose also we need adder. Then for various numerical representations are also there, like XS3 code, okay, binary coded decimal code. For all of them we need adders. Okay. Now what is half adder and what is full adder circuit? So the half adder circuit has two inputs A and B, which add two input digits and generate a carry and sum. So our half adder circuit has how many inputs? It has two inputs A and B, and it generates the carry and sum. The full adder circuit has three input numbers and generates a carry and sum. And the three inputs are A, B and C. So what you understood? From half adder circuits, we have only two inputs and we have two outputs, carry and sum. And full adder circuit has three inputs, A, B and C. But it again has two outputs, carry and sum. Now half adder. So half adder adds two binary digits, where the input bits are termed as AND bits and addend bits. And the result will be two outputs. One is sum and other is carry. So what are the input of half adder? Two binary digits, a single bit. Okay, two single bits are input to a half adder. And bit value, what it can be? 0 or 1. Perform the sum operation, XOR is applied to both the inputs. Now we will see how the XOR gate is used in order to evaluate the sum operation. An AND gate is applied to both the inputs and carry is produced. And for the half adder, we have AND gate in order to get the carry value. We have the XOR in order to get the sum value. So here is the circuit of the half adder, two inputs A and B, both are single bit input. We will get the output sum and carry. And here is the XOR gate and here is the AND gate. And here is the truth table. You see in the truth table we have on one side the input and in other side we have the output. Outputs are carry and sum. Inputs are 0, 0. This will give the carry as 0, sum as 0. 0, 1. It will give carry as 0, sum as 1. 1, 0. It will give carry as 0 and sum as 1. 1, 1. It will give carry as 1 and sum as 0. For half adder, it can be written as 2 bits. 0 plus 0, 0, 0. 0 plus 1 is equal to 0, 1. 1 plus 0 is equal to 0, 1. And 1 plus 1 is equal to 1, 0. This is how the output comes. The simplest expression for sum and carry is written as, sum is written as A exclusive or B and carry is written as A dot B. So sum can be written in terms of basic AND, OR and NOT gate as sum is equal to A bar dot B plus A dot B bar. So half adder IC number. So now we will look into the IC number for the half adder. So how the implementation of the half adder is done? It is done through high-speed CMOS digital logic integrated circuit. Now, this high-speed digital logic integrated circuit has the series that is 74HCXX, and that includes SN74HC08, bracket I have put 7408, and SN74HC86, bracket I have put 7486. So these IC chips are used for half adder. Limitation of half adder. Now we will see the limitation of hard adder. So half adders have a major limitation in that they cannot accept a carry bit from a previous stage. So the half adder only has two inputs, A and B. It doesn't accept the carry generated from the previous stage. That they cannot be chained together to add multi-bit numbers. This is the limitation of the half adder. In real life scenarios, what happens? We have the multi-bit numbers that are required to be added, and that thing cannot be accomplished with the half adder because half adder doesn't have the provision to add the carry generated from the previous stage. Now we will look into the full adder. The full adder has three inputs and two outputs. Okay, the first two inputs are A and B, and the third input is actually the input carry C in from the previous stage. So here is the inputs and here is the output for the full adder. A, B, C in, C out and S. So 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1. This is the output C out and S. Now, with the explanation of full adder and the truth table, the implementation of the full adder circuit can be understood very easily. Okay. So, the sum is produced in two steps. We saw the truth table. So, sum is produced in two steps. First step is that by XORing the inputs A and B, and then the result of A XOR B is then XORed with C in. We will see. So here is the sum. Okay. XOR all the three bits 0. Now second is for 0 0 1 XOR A and B 0 0 0, and 0 is XORed with 1 1. Okay. For 0 1 0, 0 and 1 is XORed 1. 1 and 0 are XORed 1. 0 1 1. Even number of ones for sum is 0. For 1 0, again XORing, I will get 1. 1 will XOR with 0, then I will get 1. For 1 0 1, 1 is XORed with 0, I will get 1. 1 is XORed with 1, I will get 0. For 1 1 0, 1 1 is XORed, I will get 0. 0 is XORed with 0, I will get 0. For 1 1 1, okay, 3 ones are there. First of all, A and B are XORed. 1 1 even number of ones. So 0. 0 is XORed with C in 1. So 1. So for some C out is true. Means C out is 1 only when either 2 of the 3 inputs are high. Then the C out will be high. So we can implement a full adder circuit with the help of two half adder circuits. We will see the C out. See from the truth table at what point C out is 1. You see here 2 inputs. Of the 3 inputs are 1. So C out is 1. Again at this point of time 1 0 1. Again 2 inputs of the 3 inputs are 1. So 1. Again here 2 inputs of the 3 inputs are 1. C out is 1. All the 3 inputs are 1. So C out is 1. Full adder circuit can be implemented with the help of two half adder circuits. We will see the diagram here. A and B are the 2 inputs. They will go to the XOR. Output will come from the XOR. And A and B are the 2 inputs for that. AND gate is there. The output of the XOR will give the sum. And output of the AND will give the carry. But for 2 half adders, you see some bit from this particular XOR will go to the next level XOR. Another input of XOR is C in. Okay. and they together will give the output, the sum for the 3 bits. Now you see this particular sum from this XOR will go to the AND gate and Cin will go to the AND gate. Together they will give the output. Both the AND gate output are odd and I will get the Cout. With full adder, we can add 2 bits together taking a carry from next lower level of magnitude. So now for multi-bit operation, each bit must be represented by a full adder and must be added simultaneously. You see the difference between half adder and full adder here. What we understood, for half adder, we have only 2 inputs and 2 output. There is no provision to add the carry from the previous stage or from a next lower order stage. But here the particular limitation of half adder is nullified. Okay. And here we have the 3 input and one of the input is actually the carry from the previous stage. Now we will see the half adder and full adder using the K map, that is the Carnot map. We will see the Boolean expression for them derived from the K map. So the sum and carry outputs of the half adder can be obtained with the help of K map. So the half adder and full adder Boolean expression can be obtained to the K map. So here is the Boolean expression. You see 2 inputs A and B. So you see A naught A, B naught B. Here sum is coming as A exclusive or B. You see all other outputs are actually 0. For only AB it is 1. So carry is A dot B. Here you see the truth table of the half adder. The carry is 1 when A is 1 and B is 1. For rest of the cases carry is 0. And sum is 1 only when A is 0, B is 1, A and next stage is when A is 1 and B is 0. So this is how the carry we derived. Okay. For A is equal to 1 and B equal to 1, carry is 1. Rest of the cases the carry, that is the Cout, is 0. So from K map C is equal to A dot B. Now we will see for the full adder K map. So for we have the 3 inputs. Okay. And this is how we make the boxes for the 3 variable K map. A bar, A. Here it is B bar, C bar, B bar, C, B, C, B, C bar. Okay. Now from the truth table you see what are the cases for sum is equal to 1. You see for 0, 0, 1. Okay. It is 1. So 0, 0, 1. At this particular stage it is 1. Then again sum is 1 for 0, 1, 0. You see again it is 1 for 0, 1, 0. That is for 2. 2 input. Then sum is 1 for 1, 0, 0. That is the 4 input. Okay. Sum is again 1 for all 3 ones. That is 7 input. Okay. A, B, C. When they are all ones, at that time sum is 1. So you see here 1. So here it is put as sum is put at A exclusive or B exclusive or Ci. That is C in. Carry from the previous stage. Now see the K map. This is for Cout of the full adder. You see? So Cout. So when it is 1, you see what are the conditions? When A is 0, B is 1, C in is 1. That is the input 3. Then Cout is 1 for 1, 0, 1. That is input 5. It is 1 for 1, 1, 0. Input 6. Again Cout is 1 for 1, 1, 1. Input 7. You see. So here 0, 1, 2, 3. For 3 it is 1. Okay. 4, 5, 6, 7. For 5 it is 1. For 6 it is 1. And for 7 it is 1. So Cout is coming as AB. After regrouping 2 boxes, adjacent boxes, I am getting AB plus B C in plus C in A. This is the Boolean expression for the Cout of the full adder. Now carry look ahead adder. We will not go into the detail of that, but we will look why we go for carry look ahead adders. So in the concept of ripple carry adder circuit. What is the ripple carry adder circuit? What happens? The output of the full adder is come as sum and carry. When this carry goes to the next stage of another full adder, which is already having the input A and B available with it, and it is getting the carry from the previous stage, it will give again the sum and carry, and then that carry will be carried forward and will go to the next stage of the full adder. So it is going like a ripple. From the lower stage, it is going to the upper stage. Okay, and there is a propagation delay in that. Immediate output of the full adder won't come. Immediate sum and carry won't be generated from a full adder unless or until the Cin, that is the carry input from the previous stage, is available. So because of the propagation delay only, carry look ahead adders got into existence. So in the concept of ripple carry adder circuit, the bits that are necessary for addition are immediately available. Whereas every adder section needs to hold its time for the arrival of the carry from the previous adder block. So that is what I spoke. A and B input are already available, but we have to wait for the Cin. Hence, it takes more time to produce sum and carry as each section waits for the arrival of the input. So, for instance, to deliver the output for the nth block, that is the nth block is the nth full adder. It needs to receive input from n-1 block. So, for nth block, in order to evaluate the sum and carry, the nth block need to have the carry generated from the n-1th block. So, there is propagation delay. To overcome the delay in ripple carry adder, a carry look ahead adder was introduced. So, it has here by using a complicated hardware, the propagation delay was minimized. So, what is the gist of the whole paragraph is that the carry look ahead adder came into existence in order to remove the limitation of ripple carry adder. If you like the video, share with your friends, subscribe the channel. Have a nice day. Bye-bye.